In today's note, we're going to look at more measures of spread, specifically z-scores or z-scores and standard deviation. So what standard deviation is? Standard deviation is the average distance of the data from the mean. In other words, it's the square root of the variance. But basically what standard deviation means is the larger the standard deviation, the greater the spread from the mean. So the higher the standard deviation, the more the data is spread out away from the mean or the average. Again, similar to our last examples, we have two measures or two formulas for standard deviation, one looking at the population and one looking at the sample. Again, the formulas are the same, however, we're just looking at two different variables. So again, what these variables mean are x is each data value, our mu is our population mean, n is the total number of data, and then we have our symbol for it. Sample standard deviation, same thing. X is each data value. We have to do n minus 1 for our total number of data. And x bar, again, we've talked about x bar, is our sample mean. So the sample mean results in a slightly larger deviation, and the reason for this is that since it's only based on a sample of the population, it tends to underestimate the true deviation. So again, it's taking into account that we're taking a sample of the population, so it won't represent the population fully. In this description or this diagram of a normal distribution, this represents or shows what standard deviation actually represents. So we have our mean in the middle, as we talked about before, and down here at the bottom, this is basically one standard deviation away. And two standard deviations at 3, and so on. And what the percentages represent is what percentage of the data would be underneath or would be contained within one standard deviation in either direction, and so on. So one standard deviation in either direction would contain about 68.2% of all of our data. Two standard deviations away would be 68.2 plus 27.2%, and so on. So this is just a representation of what the spread or what standard deviation looks like on a normal distribution. If we're finding the variance is just another measurement or measure that we can use to analyze data, and the variance is the average squared differences of the scores from the mean, or basically what it's saying is the square of the standard deviation. So again, because we had two different variables representing population standard deviation and sample standard deviation, we have two different formulas for population variance and sample variance. Finally, our z-score or z-score. The z-score is something specific to each data value, and it tells you how many standard deviations a data value lies from the mean. So if you had a single data value, you can see how far away from the mean it is based on standard deviations. And again, because we have different formulas or different variables for population and sample, we have two different formulas. However, they're basically the same thing. X again is a data value. Mu is our population mean. And here is our population standard deviation. For sample, again, X is the data value, X bar is our sample mean, and S is our sample standard deviation. So again, the same formula, just slightly different variables. So in our first example, Felix and Melanie are laying down tiles. They recorded the number of tiles completed after each hour for 6 hours of work. So A wants to know who did more work. Well, you could look at it, and you could look at Felix, and you could look at how many tiles he laid over the 6 hours. So there's 34 plus 41 plus 40 plus 38 plus 38 plus 45 equals 236 tiles. So we could break that down into a rate. So 236 tiles per 6 hours works out to about 39.3 tiles per hour. And finally, for Melanie, we can do the exact same thing. We can add up how many tiles she laid down. So 51 plus 28 plus 36 plus 44 plus 41 plus 46 works out to about 246. So you can already see that she's laid down more tiles. So when we go and find her rate, 246 tiles per 6 hours works out to 41 tiles per hour. So looking at this, we could argue that therefore Melanie does or did more work. She laid down more tiles per hour than Felix did. Although it is close, we can argue that Melanie did more work. However, what we may want to consider is who was more consistent. So this is going to be finding the standard deviation. So we know how much, or on average, how many tiles that each of them were laying, but we want to know who is more consistent. So this is where we're going to find the standard deviation, and we're going to first figure out how to do it by hand. So first thing we want to do is we want to look at finding the mean. So the sum of x, or the sum of each data point divided by n, which we figured out. So we're going to look at Felix first. So we're going to do Felix's by hand. So we got 39.3, and this we got from A above. Now what we need to do is create a deviation table. So we have to look at each value. So the tiles placed, each data point, so 34, 41, 40, 38, 38, 45. Our deviation is not mu, but it's x minus mu. So we have 34 minus 39.3. Then we have 41 minus 39.3. So basically you're taking each data value and subtracting the mean from it. So we have 40 minus 39.3, so we get 0.7, negative 1.3, negative 1.3, and 5.7. Then we take our deviation and we square it. So we get 28.09, 2.89, 0.49, 1.69, 1.69, and 32.49. Now the key thing here is because we are squaring it, this entire table, or this entire column, should have no negatives. Now it's okay that the deviation has negatives, but for when we square the deviation, we want to make sure that there are no negatives. So make sure you're using your calculator correctly. Finally, what we have to do is we have to add all of our values up. So we're going to take all of these values, add them up. Or basically what we're doing is finding the sum of x minus the mean squared. So we're taking all of these sums, we're adding them up, and it works out to 67.34. So after we've done this deviation table, we can go through and now calculate our standard deviation. Because we figured out this entire first part of our standard deviation from the table, we can now just sub that value in. So it's the square root of 67.34 divided by 6, which works out to the square root of 11.223. And because we're square rooting this number is actually our variance. So just another measure. And so when we square root it, we get that our standard deviation is 3.35. So that's our standard deviation for Felix's work. Now, we can argue that that's fairly large. That means a lot of his values are spread out. But let's compare this to Melanie's. So when we go through, we can do this on a graphing calculator as well. So we're going to do Melanie's on a graphing calculator so that we can save some time. So what we want to do is when we are on our calculator, our graphing calculator, and we go to Stat and then Edit, in our first column we are going to enter all of our data. Now depending on what calculator you use, you can see the one to the right. It may look a little different, but as long as you enter the data correctly, your graphing calculator can figure this out. Once you enter all your data, you're going to hit Stat again and scroll down to the Calc menu, select one variable statistics or one var stats, then L1 and enter. And again, depending on what calculator or graphing calculator you use, you may have to go through some different steps. What you should get though is a printout or a window that shows all of these values. So we have our X bar, which is our mean. Our mean, we have the sum of our X's, the sum of all our data points, the sum of values squared, we have our sample standard deviation, we have our population standard deviation, and we just have our total number of data points, or total number of data. So again, and you can see by the calculator, you should have the same values. So what you should get is that the mean is 41, the sum is 246, sum squared is 10,414, the sample standard deviation is 8.099, the population standard deviation is 7.39, and our N is 6. So looking at the two standard deviations, we have Felix, who had a standard deviation equal to 3.35, and we have Melanie, whose standard deviation as we found, and again we're using the population one because we're not taking a sample of anything. This is our population right here, these two individuals. So Melanie's was 7.39. So since Felix's standard deviation was smaller, his data is more clustered or is more contained around the mean. So his data is clustered around the mean, which means that he's more consistent. So it's less spread out. So therefore, he's more consistent. So that's how you would use standard deviation to compare a couple values or two individuals. Again, if we have group data formulas, so this is where if you had a frequency table, you can do the exact same thing. However, you have to make the same change that we've done in the past. You have to take the midpoint, or use the midpoint, and when you take the midpoint, multiply or subtract it from the average, again that's our average, or the mean, you have to multiply it by the frequency. Because again, it would be the same thing as doing the value minus the mean, and then you have to go through the steps and square it, but then you have to multiply it by how many times that occurs. It could be the same thing as doing that data value over and over again for the number of times it occurs. And it's the exact same thing with the sample. Our mean, our frequency, and our midpoint. So again, the key thing is just make sure you use the midpoint instead of x, and you have to multiply by the frequency. However, with the graphing calculator, you can enter the x values or the midpoints in the L1 and the frequency in L2, and it should calculate that for you. Again, depending on what type of calculator you use, you may have to adjust your methods. So in example 3, a railway line gives out small bags of peanuts that don't always contain the same number of nuts. The following table represents a sample of 31 bags. We want to determine the sample mean and standard deviation using the graphing calculator. So again, this would be an example of a frequency table where we would have to go through and use those steps above. But with our calculator, what we can do, if we go to stat, then edit, we can enter the number of nuts, so the first column, into L1, then we enter the frequency into L2. As you can see by the calculator, we have the number or the value and then the number of times it occurs in the second one. So that's the same as your L1 and L2. We want to press stat again, scroll to calc menu, select one vars or one variable statistics, then L1 and L2, and enter. Keep in mind your L2 is your frequency list. So again, you have to make sure you remember these steps. And when you go through, you should see that the mean is 30.35, the sum is 941, the sum squared 28,607. The sample standard deviation is 1.19856. The population standard deviation is 1.17907, and the sum, or sorry, the total number of data points should be 31. So from this, we found that our mean, or our x bar, is equal to 30.41 nuts, which is good. And then we have our standard deviation, which works out to about 1.2 nuts. So with this, we can then say whether the data is spread out or not. We know the average, so we can come up with some analysis there. What we want to do now is we want to calculate the z-score of a bag that had 31 nuts and interpret the meaning. So if I use my z-score, it is x minus x bar, or the mean, over the standard deviation. So we have z is equal to 31 minus 30.4 divided by 1.2. So my z-score is equal to 0.5. So therefore, what this means is a bag with 31 nuts is 0.5 standard deviations from the mean. So you would say that this is fairly close. So calculate the z-score of a bag that had 29 nuts and compare its distance to that from the mean to that of 31. So again, you're going through the same thing, finding your z-score. 29 minus 30.4 divided by 1.2. We get a z-score is equal to negative 1.2. So what this means is a bag with 29 nuts is 1.2 standard deviations before the mean. So the negative doesn't mean that it's lower or anything. It basically what it means is that it's below or before the mean. So it's going, which makes sense because we know the mean is 30.4. 29 is going to be lower, but we're looking at not so much the difference. We're looking at how far away from the mean it is. So we know what the standard deviation is. If we compare it back to 31, the standard deviation we got there, we could say therefore 29 nuts is further or more spread out from the mean. And finally, the packaging company rejects any bags that are filled with less than 3 standard deviations below the mean. Which bags would be rejected? So in this case, we are still using our z-score because the z-score can help us figure out what is, or what the data value we're looking at. So z minus x minus, or z equals x minus x bar divided by standard deviation. And the value that we're looking for is this value. We want to know what is 3 standard deviations below the mean. So in our formula, because it's 3 standard deviations below, that means my z-score is going to be minus 3. The minus for below the mean, the 3 for the 3 standard deviations. So this equals x minus 30.4, because again, I'm looking for that x value, divided by my standard deviation of 1.2. And now when I start to solve, negative 3 times 1.2 equals x minus 30.4. I get an x value 26.8. So therefore, any bag with fewer than 27 nuts will be rejected. And again, you could figure the same thing out by, if you wanted to figure out 3 standard deviations above the mean, you just have to change it to a plus. So again, from this note, the key thing is just understanding what standard deviation means, how to calculate it by hand and by calculator, and then being able to find the z-scores and interpreting what the value means.